Hello. Today we're going to talk about equilibrium point analysis. Before we do so, let's review some ideas from before about the Tacoma Narrows Bridge. In 1937, the Washington State Legislature decided to build a suspension bridge just north of Tacoma. It would be the longest suspension bridge in the world. Unfortunately, by November 1940, this bridge collapsed. We're motivated by the following question. Can we explain mathematically why this happened? Well, for the first 4 months the bridge was in use, from July through October of 1940, the bridge would typically undergo an undulating motion. However, a new form of motion appeared on November 7th of 1940, namely a twisting motion. In order to understand mathematically what happened, we will introduce two variables in order to differentiate between these two motions. First, we can consider the height y of the center of the bridge, and second, we can consider a twisting angle theta. In the late 1990s, McKenna considered these two variables and proved that they are both solutions to second-order linear equations. That is, the variable y has an equation of the form y double prime plus p times y prime plus q times y equals some forcing function g of t, and theta double prime plus capital P times theta prime plus capital Q times theta equals some forcing function capital G of t. We can consider two extreme cases of this motion. First, let's say that there is a light wind which makes the bridge gallop but not twist. This means that we can write our forcing function, lowercase g of t, as negative g plus lambda sine mu t, while the forcing function capital G of t equals 0. We found that y of t equals a constant, negative g over q, plus a periodic function, a sine omega mu t minus phi, and theta of t is the constant that's 0. That is, y of t is a periodic function that oscillates around negative g over q, while theta of t is a constant function. This actually explains the galloping motion that the bridge underwent for the first 4 months. Next, we can consider the torsional motion. That is, say that there is a faster wind which does not make the bridge gallop, but does cause twisting. We can write this as saying capital G of t equals lambda sine mu of t, while lowercase g of t equals a constant, negative g. We found that y of t equals a constant, negative g over q, while theta of t is a periodic function, capital A sine mu t minus capital phi. This latter phenomenon is what's called aeroelastic flutter. As a remark, both of these functions are just approximate solutions, assuming that the height y and the twisting angle theta are small. The actual equations used to model the motion of the Tacoma Narrows Bridge are actually linear, which you can see here on your screen. This is all in terms of the function r of u, which is the minimum of u and 0. One can only solve such differential equations, unfortunately, using numerical techniques. Today, we're going to talk about equilibrium point analysis of a system of equations. As a reminder, say that we have a two-dimensional system of differential equations in the form dx dt equals f of t, x, and y, and dy dt equals g of t, x, and y. Recall that this system is said to be autonomous if f and g are not functions of time. A point, capital Y sub 0, is said to be an equilibrium point if f of that point equals 0 and g of that point equals 0. So that capital Y of t, which equals that constant point, is called an equilibrium solution. We've seen many examples of autonomous equations where we have actually found the equilibrium points. We list a few of them now. First, we have the Lotka-Volterra predator-prey model. Let's say that y of t denotes the size of a population of predators at time t, and x of t denotes the size of a population of prey at time t. Then dx dt equals alpha x minus beta xy, and dy dt equals negative gamma y plus delta xy. We found before that there are two equilibrium points. namely y sub 0 equals the origin, 0, 0, or y sub 0 equals n sub x and n sub y, where n sub x and n sub y we can write in terms of the coefficients alpha, beta, gamma, and delta. As a slight generalization, let's consider the predator-prey model as before, but say that we have perhaps carrying capacities m sub x and m sub y. Then dx dt, we have alpha times 1 minus x over m sub x times x minus beta xy, and dy dt equals negative gamma times 1 minus y over m sub y times y plus delta xy. More generally, in this case, we have four equilibrium points, namely the origin, 0, comma m sub x, comma 0, or n sub x, comma n sub y. Next, we consider the van der Pol oscillator. Recall that this is a differential equation we find by attempting to model the rhythm of the heart in terms of its electrical impulses. In this case, we have a differential equation in the form dx dt equals y and dy dt equals negative x times mu times 1 minus x squared times y. We found that there is just one equilibrium point, namely the origin. And finally, we considered linear systems with constant coefficients. Assuming that we have constants a, b, c, and d, we can consider the system dx dt equals alpha times x plus beta times y, and dy dt equals c times x plus d times y. Assuming that the determinant AD minus BC does not equal to 0, then we found there is just one equilibrium point, namely the origin. Let's consider a special example to get a better idea of what's going to happen today. Say that we have the following two-dimensional system. Dx dt equals negative 2x plus twice x squared, and dy dt equals negative 3x plus y plus 3x squared. We claim that there are two equilibrium points, namely y sub 1 equals the origin, and y sub 2 equals 1, comma 0. We can find these by simply setting dx dt equals to 0 and dy dt equals to 0. What's of more interest to us are the phase diagrams to explain the behavior of the solutions. Here, we're simply plotting the slope fields. That is, given a point x, comma y, we can plug in the values to the systems above to find a vector in the direction 2x plus twice x squared, comma, negative 3x plus y plus 3x squared. When we connect all of these arrows together, we then see the blue lines that you have here on your screen. Notice that the circles are actually around the equilibrium points 0, comma 0 on the left and 1, comma 0 on the right. Here, we're zooming in very close to the equilibrium points to get a better idea of the behavior of our solutions. Notice that on the left, near the origin, 0, 0, we actually find a saddle, whereas on the right, near the point 1, comma 0, we find a source. This gives us a large motivating question. We know how to classify the equilibrium point, namely the origin, for a linear system with constant coefficients. But can we do the same classification for any two-dimensional system? Here on your screen, you can see the classification that we determined in previous lessons, where we have the so-called trace determinant plane. If we consider the trace and the determinant, then we can determine whether we have real distinct eigenvalues, real repeated eigenvalues, or complex eigenvalues. From these, we then have classification of the various equilibrium points. Either the equilibrium points will be saddles, sinks, sources, spiral sinks, centers, or spiral sources. Here's our main result for the day. Say that capital Y sub 0 is an equilibrium point for our autonomous system dx dt equals f of xy and dy dt equals g of xy. We can classify the equilibrium points capital Y sub 0 via the eigenvalues of the following 2 by 2 matrix capital A. df dx evaluated at capital Y sub 0, df dy evaluated at capital Y sub 0, dg dx evaluated at capital Y sub 0 and dg dy evaluated at capital Y sub 0. We'd like to quickly explain why. First, let's consider a Taylor series expansion around this equilibrium point. Here, we're considering an expansion, but in terms of the two variables x and y. That is, we can first express f of xy as f evaluated at capital Y sub 0 plus the partial derivative df dx times x minus x naught plus the partial derivative df dy times y minus y naught, and so forth, higher order terms. Recall now that f of x naught y naught equals 0. We can write the same expression for g of xy. Now let's make a change of variables. Let's denote u as x minus x naught and v as y minus y naught. Recall that f evaluated at capital Y sub 0 is 0, so we see that du dt equals partial of f with respect to x times u plus partial of f with respect to y times v plus higher order terms. Similarly, dv dt equals partial of g with respect to x times u plus partial of g with respect to y times v plus higher order terms. This means that we have the following approximate expression for the derivative of the vector uv. We can write this as d by dt of uv is approximately the matrix A, B, C, D times the vector uv. Here, we've expressed A, B, C, and D in terms of partial derivatives evaluated at the equilibrium point, capital Y sub 0. This 2 by 2 matrix is called the Jacobian matrix of the system at our equilibrium point. The linearized system from our two-dimensional system can be expressed in the form dy dt equals a times y, where y is the vector uv, which we can write as x minus x naught, y minus y naught. And capital A is the matrix from before. It's really the matrix lowercase a, b, c, and d. As a remark, remember that if we analyze the eigenvalues and eigenvectors of this 2 by 2 matrix A, and then refer back to the previous table, then we can classify the equilibrium points capital Y sub 0. We'll end today's lesson by going over a few examples. First, let's consider the van der Pol oscillator. dx dt equals y, and dy dt equals negative x times mu times 1 minus x squared times y. First, we have the functions f of xy equals y and g of xy equals negative x plus mu times 1 minus x squared times y. We can compute the partial derivatives to find that df dx equals 0, df dy equals 1, dg dx equals 1 plus mu times negative 2x times y, and finally dg dy equals mu times 1 minus x squared. Recall that there is a unique equilibrium point that is the origin. This means that we have the following Jacobian matrix. Capital A equals 0, 1, negative 1, mu. We can then compute the eigenvalues as lambda equals mu plus or minus the square root of mu squared minus 4, all divided by 2. If the absolute value of mu is less than 2, we find that there are complex eigenvalues, so we expect to see spirals. In fact, if mu is negative, this is the real part, then lambda here will give us spiral sinks. And on the other hand, if mu is positive, then we expect to find spiral sources. Here are some examples of graphs that we saw in previous lessons. The two at the top correspond to mu is equal to 0. These are exactly when we have centers. Notice that we have spirals, but they are neither spiraling in towards the origin nor spiraling away. At the bottom, we have mu is equal to 1. Again, we expect to find spirals, but because mu is positive, we have a spiral source. Notice that if we zoom in very, very close to the blue dot on the lower right-hand part of your screen, you'll see that it does look like we actually do have spiral sources. As a second example, let's consider the system dx dt equals negative 2x plus twice x squared, and dy dt equals negative 3x plus y plus 3x squared. First, we have the functions f of xy and g of xy as you see, and we can compute their partial derivatives. We find that df dx equals negative 2 plus 4x, and df dy equals 0. Similarly, dg dx equals negative 3 plus 6x, and dg dy equals 0. We found that there are two equilibrium points for the system, namely the origin, 0, 0, and 1, 0. Evaluating the first point for our Jacobian matrix, we find the matrix capital A is negative 2, 0, negative 3, and 1. The eigenvalues of this are lambda 1 equals negative 2 and lambda 2 equals plus 1. Since we have real numbers that have different signs, we find that near this point, the origin, we should have a saddle. On the other hand, let's consider the next equilibrium point, namely 1, 0. We find that our Jacobian matrix, capital A in this case, is 2, 0, 3, and 1. The eigenvalues now are lambda 1 equals plus 2 and lambda 2 equals plus 1. Here we have distinct eigenvalues, but actually they are both positive. That means we'll find a source. In fact, the corresponding eigenvectors are 1, 3, and 0, 1, so you can actually see the directions in which we flow along these sources. Here you can see an explanation of the graph that we found earlier. Again, the one at the top is simply the phase diagram, which really comes from the slope field. But you can see that for the circle on the left, this is the close-up of the origin y sub 1 equals 0, 0. We indeed do find a saddle. On the right, you can see the close-up of the point y sub 2 equals 1, 0. And here, indeed, you can see that we do find a source. Thanks very much for watching.